Yeah, so let's start with the energy simulation workshop uh, worked by the Hypergrid and several sister projects. Now we will start with Diamond project presented by Sergio. Okay, so go on.
Okay, good afternoon, everybody. Thank you for introducing. I will explain one of these projects in the context of simulation and standards for simulations in terms of energy. The project that I will introduce is the Diamond project. This is a Horizon Europe funded project. It is focused on the dynamically managed self-cooling high-performance computing data centers. The idea is to introduce and develop innovative and efficient cooling systems supplemented by active management of the data center. The idea is to introduce optimal dynamic operational conditions with the power of simulation tools in order to optimize the energy performance of the data centers. We have a very important consortium. The idea is to involve big data centers, and it was possible. And now the consortium is managed by IDP, the company I work for. Desorption Technologies, this is a German company which is going to develop the cooling systems. The rest of the partners, as you can see, the idea is to use or to apply the technology in two important data centers, one in Torino and the other one in Barcelona, which is the Barcelona Supercomputing Center. The idea is that we can demonstrate this simulation power in these two data centers. As you can see, the Barcelona Supercomputing Center is able to manage a lot of information, producing a lot of heat, which will be used to be reused. The idea is to use the waste heat produced by data centers. This is a very big computing center in the world. The other one is the High Performance Computing Center in Torino. Both of them represent a big challenge to demonstrate the Diamond concepts to be developed. Which are the solutions we are going to demonstrate? First of all, we will try to apply the power of simulation with a concept of SimBot, which is trying to get information from the architecture of the building where the data center are located, with the different installations and components. This can be linked to an energy simulation system. We are going to use tools like EcoSim Pro in order to combine IFC models together with the mathematical models in order to produce the simulations in real time. The idea is to make real-time simulations that will be used like baselines for further adjusting and optimization processes with the current control systems in the data center. The idea is to improve the software time frame in order to produce real-time simulations in milliseconds. We also will demonstrate that the combination with the SCADA control systems, we can also compare this time frame basis. And obviously we have to provide to the operators of data centers enough information to try to adjust these parameters in minutes. This is more or less the idea. So we are trying to provide real time between control systems and and direct cooling operators in a time frame from 5 to 10 seconds until 5 minutes. Another output of the project is the use of tools for the simulation. As I mentioned before, real-time simulations, this is the main idea. To use standard libraries. Standard libraries not only for the architecture models. Obviously here we are going to use IFC to make the geometric, and also we can include geographical parameters in order to see the impact of environmental conditions, the building. And obviously we'll also use standards in terms of the heating and cooling international standards like ASHRAE or RIBA, okay? This is more or less the idea, the use of international standards. And finally, the benefits of the simulations are that we are going to have energy simulations for cooling for both liquid and gas in this kind of data centers. And obviously, we are going to see if electrical solutions can be also applied. Another innovation is the waste heat integration within the building. We can use it for the local needs in terms of cooling and heating, because large amounts of heat are produced in these buildings. And then we'll also introduce the electrical management in order to improve the performance. Try to get more efficiency from the electricity provided and reducing the waste heat. So at the end, the most important thing is try to improve the information exchange between the real life conditions and all of the simulated situation with the SimBots. This is the main reason of this project. And obviously we also will improve the collaboration with other participants in order to create documentation and publications to be published in different media, no? Not only at a scientific level, but also in different congresses and forums. Okay? So I think that's all from my side. I think we can take questions.
Okay, so hi everyone. First of all, I'd just like to say that this presentation should have been carried out by Sergio Costa from Typhoon Hill, but he couldn't make it due to a last-minute event. So I will be presenting. My name is Mikel Boras. I work for IDP, and I'm the project coordinator of Hybris project. Now, in a nutshell, Hybris aims at the integration of two different battery systems. One is a standard, let's say, lithium titanate battery, and the other one is an aqueous redox flow batteries. So you might wonder, what is Hybris project doing here? That's because I'll just focus on the ICT part and the simulation that happens in this project. We are 15 partners around Europe, and I'm going to focus on the activity done by namely four of these partners. These ICT tools include the Advanced Battery Management System provided and developed by CEA in France, the Integrated EMS Energy Management System in the cloud developed by Ileco, or now Augie, in Belgium, and then also the hybridization, optimal sizing, and system integration, simulation and validation. That's through basically this set of technologies you see here, but we are going to focus on these in the middle one, this hardware in the loop or HIL device and digital twin. Now, in this project, we have 3 different demo sites. One is in Messina, Italy. This is a low-income family neighborhood. And one of the most important points here is that we need the island mode use case or service to be provided when the grid falls, being an island, in Sicily. The other one is this business park in Brascat. Here it's the e-mobility hub, and we look for services such as arbitrage, peak shaving, etc., etc. And final one is this also business park in Tholen, Netherlands. This is completely virtual, so the technologies developed were tested or are being tested in the real cases, validated in the real cases, and then demonstrated in this virtual site just to check what profit or what benefits would come from potentially installing a hybrid energy system as the one we are developing here. These are the basically summary of services that are being provided in the Hybris project. Again, I'd like to stress the importance of the grid forming or island mode operation. That's important for sites that are in risk of being left without a grid. So we use this battery system to provide this grid whenever it falls. Other ones are peak shaving, arbitrage, providing an energy community, etc., etc. And on the right side, you can see basically these 3 partners or 4 partners that I was naming. Ileco, now Augi, is the cloud hosted EMS. CEA and former PowerUp provide this cloud hosted or cloud-based also advanced BMS. And then Typhoon Hill provides this hardware in the loop, software in the loop part of the equation here. I've forgotten to mention Hestec. Hestec is a Spanish company integrating everything together, at least at the battery level. So now, how does this model or simulation model work? We have the different battery models, the Aqueous Relics Flow and the lithium titanate, both developed by CEA and implemented by Typhoon Hill using the battery cell component. Then we have both inverters implemented by Typhoon Hill using this bidirectional AC-DC converter, and then the communication interfaces plus the API structure. That's done by Hestec in Spain. So we have kind of a complex ecosystem here of different companies working together basically through the cloud and aiming at simulating the battery or the hybrid battery systems behavior in a real case. So before actually working in a real scenario and then saving some costs and also risks. Once the battery model is set up, we need to build the grid or use case scenario, so that for that purpose or for that objective, we just built upon the existing grid in Messina, Italy. Here you can see just like the electric diagram. And then we went to representing this hardware in the loop model for device. So once we have all these, it means that we can test these use cases, future services of the actual real battery before it's actually implemented. So here we start having what we call this battery digital twin, with which we can carry out simulations that can just have a range of services, let's say. So these real-time models, first, what we do is these EMS development. This important thing is that we manage to, we do this while the HES is physically being installed. So we do things in advance. Now the physical installation of the HES, it takes a lot of time. The Redox flow we are talking about probably more or less 8-ton system, so it's heavy, it's hard to move around Europe, costly, a lot of controls involved, etc., etc. So while that is taking place, we start this EMS and software in the loop development, testing the control commands, so testing the control of the battery, testing, yeah, basically that, how we control this battery in case of any signals or any problems arise during the operation. Once that is ready, once the EMS is ready, we start checking the communication through or with the API that just to remember, is produced or developed by Estec in Spain, and we start testing these real-time tests of these control commands I was speaking before. Finally, we have the final tests that include the simulation of the real battery systems to validate these communication and control schemes. Now, currently, actually, as I speak, this is taking place in Messina. So we finally managed to receive this HES container, you can see, which again is quite heavy, quite difficult to move around. We received it in Messina, and it's being now installed with obvious last-minute problems due to transportation and so on. But again, while physical installation is being done, tests are done virtually through this hardware in the loop. So just to end, kind of just a nutshell of what I've explained. So we have the software in the loop and the hardware in the loop, testing the communication, the control actions, etc., etc. We have this time frame talking about microseconds, to 200 to 500 is possible. Now we are limited to this 15-minute time scale, limited by the API and EMS, but of course the real-time time frames are better and are meant for actually solving in a proper time frame actual real problems that might arise at the site level. In terms of how it can benefit from other simulations, we've talked about information passports or model passports. So here again, we could obviously benefit from battery information or battery passports and the standardization of the battery information that we need to build these models that I've talked about. Also, we could benefit from co-simulation coming from, for example, MATLAB, C code, etc., etc. Finally, and this comes from my side, from IDP, it would be, and that's one of the ideas of Hybris project, to build this digital twin, merging these battery digital twins with digital twin ideas, concepts coming from other sectors, such as the built environment. So it was an idea out of scope. We actually didn't carry it out due to time and, more importantly, budget constraints. But one of the interesting ideas that came up was the integration of BeamGIS related digital twins with these hardware and software in the loop digital twins. That's for sure an idea that we will try to exploit in future projects, but we will see what finally happens. Now, I'm happy to answer any questions regarding this, but again, I'm not an expert in hardware in the loop. Typhon Hill is the company expert in this field, but I will be more than happy to forward any questions or try to answer them. I think that's it. Yeah, thank you. You have my contact etc.
And I hope you can read through because I think the colors are slightly off. So I can go slow. No worries. So yes, Claudia Vannucchi from IFER, and today I will introduce to you the EnergyNet's view on from energy simulations to standards. And yes, as I said, I hope you can see because colors are a bit off, at least. But yes, EnergyNet is the story of a team that includes many researchers, developers, and experts in different fields. So really brief overview of the consortiums is 19 partners from 8 different European countries. So we got 6 in research and academia, 6 energy and supply services, 2 DSO that bring us the perspective of what is actually needed at the distribution system level. So they help us actually bring our solutions and see if they help them in the end. 2 software providers and 3 associations that they give us the perspective on what the consumers and customer final of the district heating and cooling or electricity grid actually needs. So yes, we have a plan to decarbonize the energy sector, at least participate into it with a series of technologies for low carbon electricity production and heating and cooling production that are connected with lots of different storage concepts or electricity to heat technologies and so on and so forth, with the aim of providing flexibility to the electricity grid for smart management, and that obviously should generate higher revenues for the multi-energy system operators and reduce the carbon emissions of the overall multi-energy system. So yes, brief overview of the concept. In EnergyNets, we deal with all of the different energy networks. So we have the electricity grid, district heating and cooling network, and the gas grid, and obviously they're connected with different conversion technologies and storage solutions. And sorry. So we're developing a series of different digital solutions that should enable the multi-energy system to provide flexibility with a series of planning and operation tools, and then the DSO to actually utilize and integrate the flexibility provided by the multi-energy system with a series again of tools. And finally, this flexibility provision at local scale, we will also analyze the market requirements for the DSO provision. So generally, lots of different tools that aim at demonstrating, for the slide, the capability of multi-energy system to decarbonize both the electricity sector and the district heating and cooling sector. And we would maximize the impact of this change to the multi-energy system by providing a, let's say, wholesome methodology for value creation assessment of sector integration, which I guess it's something that it's still missing. Everybody talks about the value that is created by flexibility and sector integration, but then we don't really assess it, so that's one of the strong assets. And yes, using mainly lots of assets related to district heating and cooling, and yes, brief overview of the demonstrators. The first one is in Milan, so it's a quite large district heating and cooling network. It's a 3rd generation. You can see lots of technologies. We have CHPs, we have large storages, we have electric boilers, heat pumps, basically anything that you can find, and the Milan electricity grid, so quite a large demonstrator. Second one is in Ljubljana, Slovenia, so also a large district heating and cooling network, 4th generation in this case, again with centralized CHP and decentralized CHP, EV charging, many different technologies. The third one is a bit of a different story, if you will. So it is in Paris. It is only 3 buildings, so much smaller size, but it's a 5th generation district heating and cooling network that uses mainly waste heat from a shopping center to provide heat to the ambient loop. And then we have 2 follow-up case studies, one in Vesteros, Sweden, and one in Cordoba, Spain. And yes, you can see at the bottom right, up corner on the right, all of the different technologies that are within EnergyNets. You see in dark blue, I know you can't read much because it's a tiny screen. The dark blue are the ones that EnergyNets is actually gonna touch, if you will, either in the demonstration phase, so actually modifying the technology, or with the simulations. And in light blue, you see technologies that are within the sites, but we won't be touching EnergyNets. So we're happy to share our coming open source model library, end of 2024, so we're still working on it, but we're getting there, for energy simulations. So basically, we see all of the technologies that I presented to you. How are we going to simulate them in this open source library? We're going to use the Panda tools. So basically, what you see here is a series of open source tools that are developed already. So Panda Power and Panda Pipes, they're jointly developed by University of Kassel and Fraunhofer IE, so they're both in Germany. And they're basically consist, Panda Pipes is everything that is pipe related, so district heating and cooling network and gas grid. And Panda Power actually simulates the electricity network. And yes, yeah, I'm really sorry that you can't read much. I don't know what happened to the presentation, but yes, they're Python-based libraries. They're fully open source, fully reusable. And what we're developing in SynergyNets, it's actually Panda Prosumer. So we're basically developing all of the models for the storage solutions and energy conversion solutions. So we're talking heat pumps, CHPs, power to gas, like anything that you can really think of that can connect all of these different networks together. And yes, it would also be all open source. So yeah, what is the scope of the SynergyNet simulations? Generally, scenario, we're thinking about a mid to long term, so 1 to 10 years, not for the simulation time, obviously, but just to have an overview of what the actual impact of our simulations and our changes to the demonstrator will have in the long-term scenarios, to test the evolution, obviously, of the energy infrastructure. So what the impact of a, let's say, a high rollout of heat pump will have on the electricity grid at a more general scale. And obviously understanding if the proposed changes that we have in the demo sites or follow-up case studies can actually improve the system flexibility, the renewable energy penetration, and at the same time reduce the CO2 emissions and the operational cost, also bringing a revenue stream for the multi-energy system operator. The example of high-level use cases, obviously we have a lot of different ones, and we couldn't fit them in such a 10 minutes presentation. So again, mid to long-term scenario, 1 to 10 years for SynergyNets. What we are testing with our simulations is changes both to the demand side and to the production side. So to the demand side, that can look like, I don't know, we're adding customers, we're adding different storage solution to shape the peak and so on and so forth. And on the production side, it can be integration of new renewable generation, PV, solar thermal, whatever you can think of, and also changes to the existing technology. So maybe there is a heat pump that it's not properly sized or whatever, we want to change it with a different heat pump that of a different size. So anything that changes both the production and the demand side, we can test it with developed models. And obviously we will assess a series of KPIs to understand whether our solutions, so the impact of our solution is actually performing better than the business as usual scenario. I feel that's pretty straightforward. How they're carried out, you're going to get a tiny sneak preview of our user interface. So it is still up for discussion whether the user interface will be open source as well. So all of the models, all of the simulations tools that we are going to use are open source, but the user interface, we still don't know whether it's going to be open source or not, but you can see here, you can add your study. And then here it's basically a little image of what can look like. So this is a piece of the Milan district heating and cooling network. So you see the line in green on the, yes, it's still green, on the image. It's basically representing a piece of the Milan district heating and cooling network. And then you see these blue dots, those would be substations. So then for each substation, you can click on the model builder here at the bottom right of the page, and that will bring you to a drag and drop interface that I couldn't show you because it's still ugly. We're still developing, so but yes, it brings you to this drag and drop interface where you can select different type of technologies and connect them together. So basically you can model your substation at your will, like it's very customizable, I would say, depending on your use. And yes, what do we think is important to standardize in energy simulation? So as I said, we're still at the very, very early stages. So we're still developing and validating the technology model and the user interface. So we haven't actually done simulations yet. So my suggestions are still for very early stages. So basically what we're dealing with is a lot of issues when it comes to data formats and pre-processing. So in the case of the SynergyNets user interface, you can't draw a line when it comes to the network, so you need to import a shapefile. So I hope everybody is familiar with the terms, I hope. And so basically we can do that, so we need the shapefile to be good quality and with all of the points actually connecting and not doing weird loops, things like that. And same for data formats, so to have a meaningful energy simulations, we have certain parameters that need to be input, really like lots of temperatures, mass flows, all of the usual things for energy simulations. So we need to be sure that they're in the right format and they actually have all of the things that we need. And what we think, what I believe it's very important, could be to have maybe general protocols and guidelines when it comes to the methodology followed for the simulation, so that it would be easier to compare one tool to the other, or to understand whether the results actually make sense once you compare them. And for the sake of comparability, also having a list of basic KPIs that doesn't need to be much, but the classic, I don't know, maybe greenhouse gas emissions reduction, renewable penetration, like all of these things that we're looking forward to when we talk about decarbonizing the energy system. So yes, this is a brief overview. I'm really sorry that the presentation doesn't look nice. But yes, I think we do questions later. So yes, if you want to follow us, you have the QR code for SynergyNet. Yep. Oh, okay. For me, it's good either way. Yeah, thank you.
So hi everyone, thanks again for being here, and also thanks to the organizers of this conference. So I'm Mohammed Safarif. I'm a lecturer at Dublin City University in Ireland, and also one of the work package leaders of the HiStore project. So the idea of this presentation is to show you the scopes of the HiStore project, and also to see together the simulation and optimization and modeling tasks in our project. So HiStore is a project of mainly energy storage. So we are 18 partners from across the EU countries. It started in January 2023, and it's a 4-year project, which is also coordinated by ARC or ARC-BCN, and also it targets the high TRLs from 4 to 7. Great, so here is the consortium of the HiStore project. Most of you know these partners, companies or R&D centers. So what are the main scopes and objectives of the HiStore project? We are aiming at developing and validating 4 highly innovative thermal energy storage systems based on phase change materials and thermochemical materials solutions. And these compact storage systems will be used for heating and cooling in the buildings, for domestic hot water, and also it will provide the hybrid services, which is also important, the integration of the buildings with the energy grid. Also, we are developing our open source multi-service platform and the aggregator. So here is just an easy overview and schematics of the HiStore project before and after the integration of the energy storage technologies. And here we have our solution when it's integrated with a smart aggregator and controllers coupled to the renewable energy generation and the grid, and also to the thermal energy storage systems. So what are our solutions? So we have a PCM all-in-one solution which will be used for heating and cooling and domestic hot water. We have a low temperature PCM which will be used for heating and cooling, a technology based on PCM which will be used for heating, and also a TCM heating and cooling, a TCM system which will be used actually for heating and cooling, which is also an innovative solution because it charges by the radio frequency. And then you see that these thermal energy storage solutions are connected to the building and to the HVAC system together with our HiStore management platform and also the aggregator. So the core of the HiStore project and the core objectives that we are aiming at are to develop a modular plug-and-play thermal energy storage solution. So it makes the integration much easier. So we also want to develop optimization algorithms that can be used for smarter control of the system together with the validation and verification tasks. We want to increase the replication and also the scalability to further improve it and to fully integrate the thermal energy storage system in the buildings and in actually the energy community. So at a higher level, the main impacts of the HiStore project will be to increase significantly the energy storage density, to decrease the capital expenditures to develop these solutions and also to install them, to improve the installation, and also to make thermal energy storage competitive when compared to the battery storage. So we have 4 main pilots across the EU. One of our pilots is in Dublin. We will install the TCM storage system which will be used for heating, and then we have the pilot in near Barcelona, Spain. Again, we'll install the TCM storage and it'll be used for heating and cooling and low temperature heating and cooling. PCM storage will be also tested in that pilot. Then we have the pilot in Stockholm. There in Stockholm at KTH, we will install the PCM storage, which will provide heating for residential building or students' residential buildings. And then another pilot is located in Langenwang in Austria. So this is, in this pilot, we'll test our PCM all-in-one solution. So you can see that we are testing these solutions in 4 different climates and locations in across Europe. Great. What are we using currently in order to do the modeling, simulation, and optimization for ontologies? So for the simulation, modeling and optimization of the thermal energy storage, we are using Dymola or Modelica. And so we are developing our thermal energy storage models in Dymola or Modelica. Any graphical user interface can be used for that. And also PCM libraries. We are also using Python It's very flexible and it's open source. It has numerous libraries that can be used for machine learning, for optimization, and it can be easily integrated, or many models actually can be embedded within Python. That is great. So we are using Daimola, Modelica, Python, and Protege, if I pronounce this correctly. And then we are using the functional mockup unit standard and the functional mockup interface standard. I'll talk about it in a slide. And ANSYS has been used for CFD analysis in one of our work packages. So I want to highlight the use of FMU in one of our presentations, at least two of the presentations. We have seen that we are using a functional mockup interface, a standard in our project. So here it's a key point now for us. And then I'll talk about also the co-simulation and optimization and model exchange using the FMI standard. Here is just a draft model of one of our pilots in OpenModelica. This model will be extended and completed. So you can see that the Modelica language can be used, so either as a programming language or a graphical-based modeling software. We are using Python libraries such as Flower for federated learning, for machine learning. It's great. We have the example here from one of our partners from KTH. We use it for data analysis to visualize perfectly and nicely the energy data. It's great. And we are using ANSYS. One of our partners at AIT has used ANSYS for CFD modeling of the PCM heat exchangers, for example. Here there is another example of the ontology of the TCM model, which has been developed at University College Dublin. So it shows the ontology implemented into Protege, but also we are developing our own ontology for the Heinz-Store project in Saref. So how does it work actually? How does the co-simulation and model exchange work in our project? So we have seen that the energy system, the models of the thermal energy storage or the HVAC system can be modeled in OpenModelica, in Daimola. So this model can be exported as FMU, and then this FMU will be embedded into our Python environment, in the Python optimization environment. So we import the FMU, which is like a black box, into Python, and then we create the interfaces using the functional mockup interface or FMI standard, and then we can run the co-simulation or optimization task. So the optimization task in Heinz-Store is based on the FMI standard and the Python libraries. They are open source and actually great to use them. What happened? So here, just it's a summary of the tools and software that we're using. Python. All of these tools are just classified under, the main Python libraries, such as SciPy or Flower framework or PSO optimization, and then for at system level modeling, the Modelica language or the Daimola GUI, and for the CFD modeling, the ANSYS. So most of these tools, especially at this part of the left-hand side, which are implemented in Python, are open source and no license is needed. So how does the FMI actually work here? So here is you can see the FMI standard, which is used for co-simulation and model exchange. Imagine that you modeled a storage system in Python or in Daimola, or you were about to import, let's say, a building model from Energy Plus. These tools, they have the capability to export the model as FMU, and this FMU can be imported into our Python environment or simply can be exchanged using the FMI. So it gives us this capability to exchange the models in a more robust way, a more flexible way. So thank you, everyone. And this is our High Store team. Any questions? Yes. Okay. Thanks. Angel is also there. Cheers. Yeah.
Pablo?
Okay. Hello, everyone. I am Pablo Vicente, engineer at the Building Digital Twin Association. We are participating in a project, Haiku IT and I'm as well, and developing or trying to develop standards applied to construction in general, following the idea of SymBots. These are the Haiku IT partners. In this project, we are representing data centers. Data centers, we saw that it could be a fantastic sandbox, as we don't have humans inside. So we are, deleting one of the important parameters in construction. But the limitation of the type of equipment and the way ventilation is done, we thought that could be a very good sandbox. So first of all, the objective of the VDTA, and this must be very clear, is standards. So we are not developing software or developing any technical stuff. So we are president of the VDTA, is the convener of the working group 9 in CEN 442. This is good for all your projects because you can be using, if you need it, the connection with this working group if you want to propose a standard or help to do it. We have developed a first paper or technical report in the language of the standardization groups. The technical report was collecting, I think it was more than 30 digital twins in construction, very different. You have to consider that there is no definition of what is a digital twin. So that was the interest of the technical report was to collect how is life, or what was people doing, as a first step to define what is a digital twin construction, which is what we are doing now. We have a new work item, and it is in discussion right now, defining what is a digital twin specifically for. Okay, we have some publications as well. Specifically for simulation, we have a white paper of the project Sphere, more or less describing what was the scope of the simulation, trying to be ambitious and trying to represent humans, fluids, and all the parameters in construction with detail and oriented to real time. It is available in the internet. We organize every year an international congress. This is going to be the 5th edition in Kaunas in May next year. The orientation of the international congress is, it is the social event of the association, of course, but we try to have discussion workshops like this one, where some ideas can arise and be creative. Okay? It is not only blah, blah, blah. We have some speakers as well. And this year we are going to have 2 new activities. One is the Scientific Congress. It's going to be supported by the University of Kaunas, and a brokerage event or a B2B event where we try to put together developers and municipalities and cities just to try to get some cooperation between. High School IT wants to develop digital twins for the IT server room and the buildings around. The data centers, as you know, they generate a lot of heat, and that is or can be profitable for heating in some times of the year. The methodology is to use Symbots and to try to standardize mathematical library components, which is a different way than using FMU. We can speak later why or why not. The standard components we are going to develop, we will create an ontology itself for describing the set of components. Okay? This could be important to ensure interoperability between other disciplines, because for sure simulation is going to be working with a SCADA system, with IoT, with other disciplines, and it is a way to be connected in a general way with all of them. Okay? And of course, the ontology is going to be used by the people doing simulation as knowledge base, as a tool. We don't know how this is going to be. The idea we have is to have like a very small ontology or controllable ontology, not a big data knowledge base. We think that it has to be maintained during time, so it takes sources, and probably it's going to be exploited somehow. So people is going to be using the knowledge base with contract or subscription or something. This is a vision for 10 years, so we have a lot of things to do. So data centers, I have said, is a good sandbox to prove the concept. Okay? Well, that's all.
Un moment.
Okay. So now I'm going to talk about Hypergrid. Hypergrid focuses in developing some ICT tools for energy simulation and also for validation of 3 technologies that were implemented in different living labs. For the sake of the workshop, I will focus only on these ICT tools that were developed. Okay, for the background of the Hypergrid, in this project, it was developed an energy management and optimization platform that allows you to draw the BINGIS model of a living lab with all the houses, all the commercial buildings, and also include the energy producers. Also integrated, this is the tool for the BINGIS toolkit that allows you to draw the different pipeline, and the existing pipeline that is in the living lab or in the district heating. Then you have the interoperable digital twin for the district heating and cooling assets. This is what allows you to create a energy asset and assign energy production, energy consumption. Then we have the exergonomic tool. This is one developed by GET. This allows you to make analysis of thermal loss in the district heating distribution, enhancing the design of the heating. For example, it allows you to optimize, for example, if you design the district heating with the right pipeline, or what would improve if we design it with bigger pipeline or smaller pipeline. What would be the benefit of this? Allows you to simulate that part. Also, we have we integrated the scenario analysis that allows you to, for example, you have the district heating. You want to add a new house. Do you have enough energy, enough voltage to add a new house? If you see that you're missing, you don't have enough energy, it allows you to integrate another energy asset and see if it's enough to supply to that new building. And then we have like a IoT enabled demand response. This allows you to have like IoT readings from the different smart sensors that are installed in, for example, in one of the demo cases that you'll see next. And then we have a grid singularity that is a peer-to-peer energy trading. For example, you can sell energy, the surplus you have from your house, to the neighbor. This project was applied in 4 different demo cases. The ones that will focus in the workshop will be the Turing one, where the ENCO 2 was implemented. This was the one that allows you to simulate the whole district. And then we have the Sonnenplatz, where we created the BingGIS model of the district, and then we use the exergonomic tool alongside the dynamic simulation tool. As of right now, the project is almost ending. At the end, we already integrated the ENCO 2 completely. We are just missing the part where we have to export it to the exterior so we can allow exterior users to use the platform. We are right now integrating the GET tool, the exergonomic. The scope of the simulation allows you to simulate the operation of the grid, how much energy is consuming, what is the stress of the grid, and how you can improve this grid. Local peer-to-peer energy trading, energy-based analysis and assessment of energy conversion. This platform is a long-term projection since it's for design phase mostly, that how to extend the grid, existing grid, and how to improve it. So the two for the simulations are the ones I already mentioned, mostly the exergonomic and the sign tool. How can I benefit? For example, leverage the existing simulation of renewable integration of energy storage, optimize overall grid performance. This will be what I mentioned, like you can add another access to the grid and how it will improve the energy performance. And also the benefits of the peer-to-peer trading. For example, one house might have like excess energy, so therefore you won't need another energy asset, but you can sell from one house to another one. Or the commerce is requiring a lot of more energy, so you can have all the houses sell the energy surplus to the commerce. And improve the energy efficiency of comparing output with similar hybrid grid model. For example, here you can see this example of the electrical simulation. Since the design tool allows you to simulate the electrical grid individually and the thermal grid. You can simulate both individually and combine. And this one is the thermal one. This is the MB Park. Here you have like, if I remember correctly, it was 10 buildings and 1 PV plant and 1 smart charging station, and you also have like a heat pump, if I remember correctly. So here you can see what is the stress for the network. That limit up.